everyone, this is Julian at Mecanum, and today we are going to talk about viscoelastic measurement, more precisely young modulus and damping loss factor measurement using ASTM E756 standard, also known as the Oberst beam method test. For those of you who are familiar with SAE standard, this is also similar to SAE J1637 standard. Actually, the SAE standard is kind of a particular case of the ASTM standard. So today we are going to focus on the more general ASTM standard. Well, first, this method will allow you to measure with accuracy and repeatability young modulus, shear modulus, and damping loss factor of your viscoelastic material. It will help reduce development time. It will also help design and simulation engineer to make better choice and provide the key parameters to input in simulation software. It will help you select material tailored to your particular application and also produce a state-of-the-art spec sheet for your customer and increase customers' trust. Finally, if you have specific regulation requirement to respect, you will have ASTM back data to do that. Now, the first thing to understand about viscoelastic material properties is that they are frequency and temperature dependent. So when the material is cold, the material is hard, the young modulus is high, and the damping loss factor is low. It's called the glassy region. At medium temperature, the young modulus starts to go down, but the loss factor increases to its optimal operating zone. Then, when the temperature is too high for the material, the molecule chain becomes loose, and then there's no more dissipation by friction. The damping becomes very low, as well as the young modulus, until it completely degrades or melts. This is the rubbery region. As design engineer, we want to make sure that the transition region fits with the temperature of operation of our application. So to perform this standard, you need several items. First, of course, you need a test bench, preferably temperature-resistant test bench. Here we use a magnetic sensor and exciter. A data acquisition system. This is a Thermal Pro acquisition system that can handle up to 3 test bench and communicate and control thermal chamber. Of course, you might also need a thermal chamber. We will see one later. A beam preparation kit. So preparing beam is an important part of your measurement. So you can have aluminum beam, steel beam, you might need root also as well as appropriate glue. So that's our kit and it includes all that. You also need a verification beam as requested in the standard. This is a precisely machined beam in steel. Okay. Also a torque wrench to make sure that you always install your beam the same way with an appropriate torque. And this is a beam preparation tool to make sure you apply an appropriate pressure while the glue you use to prepare your beam is curing. And that can last up to 72 hours and sometime more. So it will allow you to increase the accuracy of your test. So now let's jump into the example. For the example today, I will test a two-side treated beam. So the first step of this method is to select your type of beam. You have basically 4 choices: the uniform beam, the one-side treated beam, the two-side treated beam, and the sandwich beam that is dedicated to shear modulus measurement. So today we'll select a two-side treated beam. It's an interesting choice to extract high-quality nomogram because the effort on the beam is symmetrical when you excite it. For today's example, the beam is already prepared, but I will explain you the process. First, you need to measure the base beam, and then once the base beam is measured, you install your viscoelastic material on the beam. You need to make sure that you have the clearance for the root and that your material is very well installed. Also very important, the base beam need to be very well machined with sharp angle. If you have an irregular beam, it will create variability on your result. So once you have installed your material with a very strong glue, okay, you can install it on your preparation tool like this. Install the washer. And now that your beam is well installed in the sample preparation tool, you can leave it for the curing time of your glue that can be up to 72 hours, as I mentioned. As you can see, you can also prepare several beams at the same time if you want to average your results, which is always a good thing. My beam is now installed on my test bench, and my test bench is inside my thermal chamber, so I'm now ready to start the measurement. I'm in the ETAX interface. I open my project. So the first step of such project is to verify your setup. Here you have the acquisition setup, so resolution, number of average, the duration of your measurement, frequency, and the volume. Typically those are factory setted, but you can adjust them if ever needed depending on the test you're doing. Here you also have the thermal chamber setting, so I will connect my thermal chamber, okay, and now it's well connected. I have a soaking time of 30 minutes. So this is the time for the temperature to stabilize for my beam, my test bench, my sensors. Typically, it's the recommended time. Now that your hardware is set, let's jump to the measurement itself. Now I'm in the measurement list window. My thermal chamber is connected, and here you can see my support beam. As I already told you, I've already tested my support beam previously, and for the matter of the example, I only tested one time at room temperature, but when you do your real test, I strongly suggest that you test, even if it's just steel, to test it at all the temperature you want to test. So your support beam is tested at 100 degrees, and your treated beam will be tested at 100 degrees, for example. Now we'll create our measurement list. Add. So here, this is how you add measurement. First, you have the measurement name, so I will simply name it side. And then you need to select the type of beam. Here, my type of beam will be damp two-side, but as you can see, there is a support beam. If it's, for example, your support beam or uniform beam, which is basically the same thing, but for rigid material, and the one side, two side, and the sandwich. You also have the channel. So as I said previously, you can measure with up to 3 test bench at the same time. So you will set the measurement series for one test bench at a time. Here I only have one test bench connected, so I'll stick with the one test bench. Then you have the temperature mode. So you can have either a single temperature, or you can do multiple temperatures, so basically a temperature list. So today I will do a temperature list. I will go from minus 40 degrees, and I want to go up to 60 degrees Celsius, and I want to do step of 5 degrees. Excellent. And then I need to enter the physical parameter of my beam. So as you can see on this image, you need to have the height of your viscoelastic material, the width and the length. And you need to enter them here. So here my thickness is 0.8. And then you also need to enter the density. In my case, 1200. Okay, now everything is ready and I can confirm. And now, as you can see, all my list is ready to measure. So now I want to start my measurement campaign. Of course, I need to verify my thermal chamber is well closed and ready to start, and then we can select all the measurement we want to do. All right, selected all my material and I'm now ready to go. So I will simply select button start capture and my measurement will start. So don't forget to power off the amplifier, just a kind reminder. And I'm now ready to go for a coffee break, a very long coffee break in this case. Actually, I'm gonna go to sleep and I'll be back tomorrow. So the night has passed. I slept very well, thank you very much. I'm now ready and well rested to do some post-process, because even if the system worked all night for me, I still have some work to do. And that's what we are going to see together. So here I'm very happy, all my measurements are there and completed. Okay, so everything is there. And now I need to process each and every one of those measurements, and this is what I'm going to do here in the post-process viewer interface. For each and every measurement, I will need to identify the mode. So fortunately for me, in our software, we have an automatic mode detection to make the work more easy, but it's still a very good practice to verify each and every curve. And this is what I'm going to do. Now, all my curves have been post-processed. I'm now ready to do the temperature analysis. Now that all my modes are post-processed, it's now to create my solution set for each and every temperature. So I will add solution set. First, I need to select my beam, select my support beam, and for the matter of the example, I will leave the default name, solution 1. Confirm. Now I'll need to create that for all the temperature. My post-process is now complete. Now here I have basic visualization interface where I can see my modulus and my loss factor. But when it gets interesting is in the two next window that I'm going to present, the measured data window and the extrapolated nomogram window. First, the measured data. Here I have the result table. So first, from all the data that I measure from -40 to 60 degrees, I have all the results for my young modulus and my damping loss factor for all the modes. I can also visualize that with different graphs in the second window. Here I have the loss factor versus temperature, but I also have loss factor versus frequency. Same thing for the modulus. I also have frequency versus temperature. And finally, the wicked plot, a quite popular plot defined in the standard. Now that I visualize all that, I can also see the 2D surface. 2D surface is a quite interesting tool. Here you can see all the mode, and all the mode are linked with quadratic cubic spline interpolation function. And the very interesting thing is when you have missing mode. So here I'm very lucky, my material was quite nice and I was able to measure it at all frequencies and all temperatures, so I don't have any missing spot. But if I had a very highly damped material, I could really use the interpolated data. Okay, in this case it doesn't do anything, but if I had some missing spot, it would simply fill them using a cubic spline. I can also adjust the colors, change the color as well to my taste, and I also can show mouse coordinate to really have precise idea of the modulus or damping at a given frequency and temperature. Also, I have the exact same graph in 3D, so it's the same thing but in 3D to visualize it in a different way. Then I have the nomogram tool. The nomogram tool is very interesting to extract properties that you were not able to measure, either because the temperature was too high or too low, or the frequency was too high or too low, and you are, for example, in an application where you need higher frequency data. Well, you can use the nomogram to get this data. In the software you have 3 alpha functions that are pre-programmed. You have ISO, Arrhenius and WLF. Let me show you first the ISO. ISO is kind of the one-size-fits-all nomogram, and it works pretty well in most cases. As you can see in this case, we have pretty well aligned data for modulus and damping. But the most used is the WLF. WLF, to optimize it, you need to find coefficients C1 and C2. You can do it manually, but it can be quite time consuming. For that reason, we developed an algorithm that can minimize the variation between the alpha function and the measured data. So here I'm going to do an inversion on the loss factor and the modulus. I will let the software work a little and we'll see the result after. So it took approximately 10 seconds, and as you can see now, the results are very well aligned with the alpha function. And now I can extrapolate my data with good confidence. I can go in the 3D interface. Okay, and now as you can see, I did a graph that goes from 50 Hz to 20,000 Hz and cover a temperature range that goes from -60 to 100, which is way above my measurement range. So this is really the main advantage of the nomogram tool, is to go above your measurement range. And same thing as I previously shown, you have different ways to visualize it. You can visualize it in 3D here, or in 2D, more practical way for engineers to extract the data they need. Finally, once you have
done all that, you can extract your data in a pre-format Excel report. And you can see now all the test data are in a single Excel report. And you even have the interpolated data from the SAE standard. And all the graphs that I have previously shown in the user interface are here, ready for a presentation or simply to document your test.
So to sum up, characterizing viscoelastic properties using ASTM E756 is not just a lab exercise. It's a critical step to enable simulation-driven design, performance assurance, and cost-efficient product development. Whether you are engineering a vehicle dashboard, an aircraft fuselage, or a precision machine frame, accurate damping data ensure your simulation reflects reality and your product performance meet the requirement at the first time. So thank you very much for listening, and see you in the next Mecanum training video.